Okay, today is 19th of October 2020. Okay, remember we were talking about this triangle, ortic triangle, namely when we have a triangle ABC, like as in this here, ABC, when we draw this the altitude, namely AD, so that AD is perpendicular to BC and BE is perpendicular to AC, and C F is perpendicular to AB, so that, and the feet are D, E, F, and that was the ortic triangle, ABC. Okay, let's start with here. Now, let's talk about angle bisectors also. So we are talking about, remember, we given a triangle, we talked about altitudes, ortic triangle, and now we will talk about angle bisectors. So, what is an angle bisector? So let's take a triangle. Let's take a triangle ABC like this. ABC. When you draw this line segment joining A to some point of BC, so that each of these angles are the same, let's call them alpha, so that this point is, we call this point L. So if BAL is equal to LA, the angle LAC, which is the 1/2A, then this BAL is the angle bisector. Of the side of the angle A. And and here's a theorem. Let's first state the theorem and then prove it. The theorem said each angle bisector of a triangle there are three angle bisectors. One is at B and also at C. So each bisector, each angle bisector of a triangle divides the opposite side into segments, two segments, proportional to the length to the adjacent sides. What do we mean with this? We mean with this, for example, we mean if we take this angle bisector AL, then the length BL over LC is the same as C over B. So this side over that side is equal to B over C. Or C over B, sorry, C over B, not B over C. So this side over that side is equal to this side over that side. Okay, let's give a proof of this statement. Proof of this statement is that, so let's draw this angle again. It's not very good. It is not very good. So let's draw this, erase this, and then draw once again. Something like this. So that this length is alpha, that length is alpha. Suppose that this length is beta, this angle is beta, that angle is gamma. And this is BCLA. And that side is B, this side is C, and this whole side is A. And let's apply the sine theorem that we proved to the triangles ABL and ALC. ABL and LAC. So namely these two triangles, this one and the other one. So BL over from this triangle. If you look at this triangle ABL, this side is C. Then BL over sine alpha, this length, that's alpha. BL over sine alpha is equal to C over sine L, sine beta. So that is beta, sine L. And if you look at the other triangle, from the triangle, let me sketch this like this, ALC, this angle is gamma. And from this triangle, we have LC, this length, over sine alpha. This is alpha. Sine alpha is B over sine beta, sine gamma. Right? This side is B. So therefore, but sine gamma is the same thing as sine beta, because beta plus gamma is 180 degrees, so that their sides are the same. So therefore, BL is equal to, BL is C times, from this first equality, from the first equality, it is C times sine alpha over sine beta. And from the second inequality, we have LC is beta times sine alpha over sine beta. So if we divide, or I should have written like this. Okay. Yeah, if we divide BL to LC, then they will cancel. We will get C over B. And that's the proof that we wanted to prove. That's the statement we wanted to prove. Any questions? No questions. And we proved only for one side. And for example, if you do the for instead of the vertices A, if you write the same theorem for the vertices B, then what would we have? What would be the statement? So here is this is B, L, M, let's say, C, this is A. Then what would be the statement? This angle is, let's say, is the same thing as that angle. This is CA. What would be the statement? Hey, are you there? Anybody is there?
AM divide MC is equal to
AM divided by
MC.
MC
Yes.
is equal to
C divided by A.
this is little c divided by A. Yes, that's it. Good. Thanks. And similarly for the other sides. Okay. As a corollary of this theorem, we have another important theorem that that you will you know, at least from the I heard this before. So internal the internal bisectors of three angles of a triangle are concurrent. Concurrent means they intersect at the same point, right? So the three lines intersect, pass through the same point. Is a proof of this statement based on the internal bisectors. Okay. Yeah, I guess I gave a proof, but I guess we can prove it like this. Let me prove this way. So when we do this height, this is A, B, C, this is L, this is M, and let's say this is N, and we want to show that they all pass through the same point, so that these AL, BM, and CN are Syrians. And let's look at BL times BL over LC times CM over MA times AN over NB. That is BL over LC is, remember it was C over B, the first statement, and CM over MA is equal to this side A over, what was it? A over C, and AN over NB is equal to B over A. B is this side and A is that side. And when you multiply them, they are positive numbers. When you multiply them, you get 1. So by the converse of Sevas theorem, they are concurrent. So therefore, this AL, BM, these angle bisectors, and CN are concurrent. This is one proof, and this is another proof. Let me give another proof. We can just show it directly. So this is A, B, C. When we draw this angle bisector, then if you take any point on this AL, then it is the distance. So if, let's say, X is the point on even this line L, the whole line, extended line L, even you can consider this whole line on AL, its distance to AB and to C to AC are the same. So namely, when you take any point here, it is distance, this length, and that length are the same. Okay? So let's draw the one from, let me use another colors. Let's draw this angle bisector like this. This was another angle bisector. Let's look at this intersection point. This intersection point, let's call it, I guess we have a special name for this one, whatever that is. I, yeah. Let's look at this point I. So this, let I be the angle bisectors of. So let I be the angle by the intersection point. Intersection point of the angle bisectors AL and BM. So its distance, the distance from I to AC is equal to the distance from I to AB. The reason is that this AL is angle bisector, and also since BM is angle bisector, then it is distance from I to AB is equal to the distance from from I to BC, so that the distance from this point I to AC is the same thing as the distance from I to BC. And let me draw it here once again. So we have these intersection points. These intersection points. It is distance. Oops. I shouldn't have drawn the last one. Let me erase that. So the distance. So that the distance from this line segment AC, this is the same thing as the distance from this I to BC and AC. So this length is, let's say, little r, that length is little r, they are the same. So that, and also its distance to the side AB are the same, so that since the distance of I to AC and the distance of I to BC are the same, I is on this angle bisector of of C. So it is on this angle. It is on this bisector. It must be there. Okay. There are two proofs of this statement. I guess they are both nice. Okay. Next. Oh, so that let's observe. Let's write it once again. Let me draw it more carefully now. So this is A, this is B, that's C. Let me draw this angle bisectors by different colors. So angle bisectors are AL, CN, and BM. They pass through the same point. And if we draw these heights, let's draw heights, then the distance from I to that side is, let's say, R. Then it is distance of I to AB is also R. And the distance from I to BC is also R. So R is the distance. So if you, oops, not that one, sorry. It should be something like this. That's also R. Now, so that if you look at the circle, so here's the definition. The circle of radius R with center I is called the incircle. Incircle of ABC. So incircle is, so since these are the same, so that this incircle is something like this. I could not draw very well, but something like that. So this is incircle. And I is called the incenter. And also incenter, and R is called the in radius. In radius. Okay. So that's it about this angle bisectors. Now let's draw more things about incircle and X circles. There's also X circle, which I will say in a moment what that is. X circle is not the circle passing through this ABC. That was, remember, its name was, this circle, its name was, what was its name? Circumcenter. And the circle this inside, touching tangent to both sides, this is incircle. There's also X circles, which we will say in a moment. X circles. Okay, how time is it? Yeah. Okay, let's consider consider a triangle A, B, C, and its incircle. So let's draw this picture once again. So this is ABC, supposed to be a line segment. Anyway, and let's draw incircle with the red. Incircle is something like that, and that is here is center I. Its distance to the sides are R. That this point is I. And so that BA is tangent to the circle and BC is tangent to the circle, so that this length, so B, I guess I call this point X, Y, and Z, so they're perpendicular like this. BX is and BZ, so this side is the same thing as that side. So BZ is equal to BX, which I called Y, and AY is equal to AZ by the same reason. Let's call this X, and CX is equal to CY is equal to YA. CY is equal to CX. Let's call this Z. So this little Z. So that A is equal to Y plus Z. B is equal to X plus Z, and C is equal to X plus Y. So let S be X plus Y plus Z. So namely, it is A, B, C over 2. So the perimeter of this triangle divided by 2. So then we have this X is equal to S minus X is equal to S minus A, right? Is it right? X minus Y plus Z. Yeah. Let me write it explicitly. So from this equation, X is equal to S minus Y plus Z, but Y plus Z is equal to A. So that it is S minus A. And similarly, Y is equal to S minus X plus Z, and X plus Z is equal to B, and Z is equal to S minus X plus Y, which is C. Okay, and here's a theorem that the area of ABC is S times R. Okay, here's a proof. Let's look at this triangle IBC. I will not draw it once again, but let's look at this picture. IBC. IBC is, we have this triangle. So its area is y plus z, namely a times r over 2. This area is 1 over 2 a times r. A is the y plus c. Okay. Any questions? Okay. This is the area of this IBC, and similarly, the area of IC. Oh, something happened. What happened? I don't know. But now it does not write well. The area of, yeah, it's called ICA. It is 1 over 2. So ICA is ICA, and the base is B, and the height is R. And the area of IAB, area of IAB, so this triangle, now this in this case, it is C 1 over 2 C times R. C times R. And this is 3 triangles, namely we had so the area of this piece is 1 over 2 AR, area of this piece is 1 over 2 BR, area of that piece is 1 over 2 CR, so that the area of ABC is the sum of those numbers, which is 1 over 2 times AR plus BR plus CR, namely 1 over 2 A plus B plus C times R. This is R. And this is equal to S. This is S, so it is S times R as claimed. So the area of the triangle is S times R. Okay, good. Questions? No questions? Are you here? Yes. Only 19 people. 19. Okay. Next. Next, we will talk about extra costo. I guess let's try to draw with this. I have a ruler. So let me draw a triangle like this. Good. Triangle. I extended these lines also. So this is A. That is the point B, and that's the point C. We have this triangle ABC, and we extended those lines. And so if you, let me also change colors. Now, so if we divide this angle into 2 pieces, like this. So I mean, if you look at the angle bisector of this side, the other angle. so that this angle is the same thing as that angle. And similarly, take the angle bisector of this side, so that this angle is the same thing as that angle. So exterior bisectors of AC and the exterior bisector of B. So these are exterior bisectors. Exterior bisectors. These red lines are exterior bisectors. Of ABC, A, B, C. Okay, now let's say that this point is IA, that point is IB, and this point is IC. Actually, this is a quite good picture now, almost. And yes. Now, so any point on this IB, ICA, so if you look at this line, which line? Look at the line IA. The points on this IA and IC. So this line, let me extend this. Yeah, this line. If you take any point here, so since it's an angle bisector at B, I mean the angle out external bisector, then any points on this AB are equidistant from BC and CA. So namely, if you consider only this line and that line, so since IC is an angle bisector, if you take any point here, for example, it is distance to that line, and to this line is the same. And if you take a point here, it is distance to BC, and its distance to BC and AB are the same. So because it's an angle bisectors. And similarly, for IBIC. So the points on IB and IC are equidistant from, so it is an angle bisector of AB and AC. So that if you take a point here, it's a distance to this line, and that line is the same. But now, if you look at this point, AC, so that it is distance of AC to distance from AC to IC, so that the distance from IC to AC is equal to the distance from AC to AB and it's also that distance is also equal to BC by this about. So that the distance of this point to these three red, the black line segments are the same, so we have this length let's call this RC, and that length and this length are the same, so that if we draw this circle of radius RC with center IC, so this is, so we have a circle like that, and we also have similarly for IA, so that its distance from these three the three black lines are the same, so that if you look at the circle of radius with center IA and radius RA is something like this, which I could not draw well, something like that, and similarly on this side. Something like that. So it is a circle. I could not draw this very well, something like that, but it should be tangent. So it's the distance to oops. The other one was good, but this is not that good. Yeah, something like that. Okay, this is the circle of radius RB. So these three circles are called X circles. So these three circles the three circles, oh, what happened? Circles circles. Let me call. Let's give some name. This is C. Let's say A. This is the circle CB. That's the circle CC. So that the circles are CA, CB, and CC are called X circles. X circles of the triangle ABC. ABC, and these are A, are B, are C, are called X radii. The X radii. Radii is the plural of radius. Okay, one more thing is that if you look at this picture, so one more observation is that if you look at this point IB, let's look at this point IB, it is distance from BC to AB are the same, right? So this length is the same thing as that length, which I did not draw very carefully. So they are the same. So that this point lies on this bisector, internal bisector of B. So that IB lies. So IB lies on the internal bisector of B, and it's also on the external bisectors of A and C, also on the external bisectors A and C. So therefore, we have this statement. Let me state this theorem, and then I will finish. The external bisectors so we proved for ABC, but we said that for ABC, but for that it's the same. The external bisectors of any two angles for example, A and C, in the above example, are concurrent with the internal bisector of the third angle. So external bisectors of any two angles is concurrent with the internal bisectors. So namely, if you draw this, let me draw once again ABC. So when you draw this external bisector like this, and when you draw the external bisectors here and the internal bisector of this angle B, so they are concurrent, so they pass through the same point like this. I see. A, B, C. Okay, I guess that's it for today, and see you on Thursday. Let me finish this. Let me finish this recording first.